Oh, I can't possibly get enough of CeeLo Green. He's our main man. Tonight's title is an alternating series test. We're going to find it to be a very likable test once we get a couple underneath our belt. We're going to, the whole theme tonight is what do we do when we see some negative terms? So far, we've been working with series that have only possessed positive terms for the most part. There's been a few exceptions to that. However, and then today's series are going to alternate between positive and negative terms and just continue to alternate and oscillate back and forth. So we're going to jump right in it, and to kind of build our understanding conceptually, we're going to focus on the alternate harmonic series. Okay, this is another very famous series that we can refer to by name. It is what we call in the math world a celebrity. Okay, certainly very recognizable. And the alternating harmonic, okay, looks like this. Okay, we're going to start at n equals 1. I'm going to get a little sloppy at times tonight, maybe not put my index, but basically we have negative 1 to the nth power on top divided by n. So instead of just simply 1 over n, and I'll refresh your memory, this over here is what we call the harmonic, okay? And now we're introducing you to the alternating harmonic right here. And what you're going to notice as we start to expand this out, and we substitute a 1. In fact, you know what? I gotta tweak something here. I want that exponent to be n plus 1. Almost forgot to do that. Okay, so as I substitute a 1 into there, I end up with negative 1 squared on top and 1 on the bottom, so it's basically just a 1. Now, I'm going to substitute a 2 into there, and I'm going to get negative 1 over 2. And then if I substitute a 3, I get positive 1/3, substitute a 4, substitute a 5, and then we'll substitute a 6, and so forth and so forth and so forth. You can see the pattern starting to develop. Clearly, we have an alternating series. First term's positive, followed by a negative, followed by a positive, etc., etc. Now, I'm going to do a lot of graphical stuff here tonight to build us up. And the first thing I'm going to do is I want to graph just the individual terms themselves. Okay? There's n equals 1, n equals 2, 3, 4, 5, 6, 7. Okay, and these are all my n's. We'll say it goes as high as positive 1, as low as negative 1. And we're going to start to plot each individual term. So we're not talking about we're not doing the sequence of partial sums yet. We're just doing the individual terms. So I'm actually going to put a little a sub n just to remind myself that these are the terms. So there's the first term, then the second term is negative 1/2. The third term is positive 1/3, negative 1/4, positive 1/5, negative 1/6, positive 1/7, etc., etc. And you could see how the graph, so to speak, is funneling in towards the x-axis, and we're kind of converging on the x-axis from both above and below. Now we're going to up the ante a little bit more. I'm going to do one more graph, but this time I want to graph the actual sequence of partial sums. So S sub 1 is just the first term itself. S sub 2 is going to be the sum of the first 2 terms. S sub 3 is the sum of the first 3 terms. And I did a little adding ahead of time, and I got my common denominators and came up with 5, 6. So that's just a smidge less than 1. S sub 4 is the sum of the first 4 terms. I came up with 7/12. And you notice that's just a smidge bigger than 1/2. S sub 5, I ended up with 47/60, just a little less than 1. S sub 6, I came up with 37/60. Okay, and we could have kept going on and on, but I was content there at that point. And here's what the graph looks like. N equals 1, 2, 3, 4, 5, and 6. And on this axis, we're going to talk about the sum of the partial sums. We'll say 1's way up there. Let's say that's 1/2 right there. There's 3/4. There's a quarter, just to give us a little more accuracy. And we're going to start to plot these, okay? So let's see. S sub 1's right here. S sub 2's right here. Let's see. S sub 3 is just a smidge less than 1. S sub 4 is just a smidge greater than 1/2. S sub 5's there. S sub 6 looks like it's going to be about right there. And I wish we could kind of extend our graph a little bit and we'd see this funneling action, and it looks like it kind of gives the appearance that we're funneling towards some number that falls in the middle right here. And so, for instance, if we had the time and the energy, we could actually calculate the sum of the first 100 terms, and then the sum of the first 500 terms, the sum of the first 1,000 terms. And it looks like we'd be getting closer and closer to some value in here, somewhere around 3/4. It's not actually 3/4 for sure, but it's around that neighborhood, give or take a couple of tiny decimals. Perhaps the biggest thing to take away from this graph is the idea that this alternating harmonic is going to converge. It's converging to a finite number somewhere around the neighborhood of 3/4. And compare that to the regular harmonic. We've proven time and time again that the regular harmonic diverges. And now we're just getting into the tip of the iceberg with alternating series, but we've already proven that the alternating harmonic does just the opposite. It converges. Another graphical approach that I like to take on this alternating harmonic is simply in the form of a number line. Let's say I have this number line and I say, okay, there's my 0 and there's my 1, and I just want to keep a running total of my sums. And of course we notice that the first term is right here, and then the S sub 2 is right there. The sum of the first 3 terms was right here. The sum of the first 4 terms is right there. There's S sub 5, S sub 6, S sub 7, S sub 8, S sub 9, and so on and so on. And it's almost like one of those crazy dreams you used to have when you were little and the walls were closing in on you. And that's what's happening with this alternating harmonic. In fact, the real sum is happening right there somewhere. Okay, we'll call that the actual sum. It's somewhere inside there, and that's enough to convince me that this sucker really does converge for sure. The next question up for debate is, what truly is an alternating series? Is it just any old series that happens to have a negative term sprinkled there somewhere? The first one we looked at had started positive and then negative and then positive and then negative, and it continued on. Another example, if the first term was negative and then the second one would have to be positive and then they'd alternate off of that, this too is considered an alternating series. One that you want to watch out for: if I go positive, positive, and then negative, negative, and then continue to do this, positive, positive, negative, negative, that is not an alternating series, okay? In order to be an alternating series, you truly have to change signs on each and every term. Okay, we're going to go ahead and nail down our theorem tonight. Our theorem is now 9.14, chapter 9, theorem number 14. And it says, first of all, let a sub n be something that's positive, and then the alternating series, and it's going to come in one of two forms. We're going to say it could be negative 1 to the nth power times a general term, a sub n, or it might come in the form of negative 1 to the n plus 1 power. In fact, I'm going to throw in a third case. Once in a while, you may see negative 1 raised to the n minus 1 power. That's also an excellent alternating series. Now, we're going to say that these series, they converge if the following two conditions are both met. Okay, condition number 1. The limit as n approaches infinity of a sub n has to equal 0. And number 2, the n plus first term has to be smaller than or equal to the nth term, aka the terms are decreasing in magnitude. And so what we're going to do is we're going to verify that both of these conditions are met. Predominantly the first one is going to be the big one that we're going to put all of our energy into. And I'll tell you what. We've really been preaching for the past several days that you cannot use the nth term test to prove that a series converges. You can only use it to verify or prove divergence. Now, like most rules, there are exceptions, and the exception exists right here. The nth term test can be used, okay, because that's basically what we have here. Okay, the nth term test can be used to prove convergence if we are talking about an alternating series. Okay, so that is the one-time exception to that rule. Okay, here's example number 1, and what I'm going to do is I'm going to peel it apart just to make it look like a little bit more like an alternating series. I'm going to pull out the -1 to the nth power, and then we've got our 1/2 to the nth power. And of course you could verify if I multiply those two terms together, it would lead me back to the original black series there that we have written first. So now what we're going to do is, it is an alternating series. Your a sub n is this piece right here. That's your a sub n. It's the whatever's next to your -1 to the nth power. And the first condition is we're just going to take the limit as n approaches infinity of that term. In fact, I'm going to go one step further and write it as 1/2 to the nth power, just so you can verify that it truly is small over large. And because it's small over large, the limit equals 0, or we put a little smiley face there. That's a good thing. And number 2, we want to verify that the nth term, which would be 1/2 to the n plus 1 power, is less than or equal to the nth term itself. And I'm going to decompose on the left side. I'm going to say 1/2 to the first power times 1/2 to the nth power. And then I'm going to divide both sides by 1/2 to the nth power. And we're going to verify, yes, 1/2 is smaller than 1. Check. Ding, ding, ding. We have a convergent series because both conditions were met. Okay, here's example number 2, and if we politely ignore the -1 raised to the n plus 1 power, we could identify who our a sub n is, and according to the alternating series test, and I'm just going to abbreviate, you're going to see me say AST a lot. That's the alternating series test. We're going to check out the two conditions. The first one is, we're going to try to take the limit as n approaches infinity for n plus 1 over n. According to the power fight, we have same over same. Comparing the coefficients, we end up with a 1. Now, that is not equal to 0. So instantly, I do not have to waste my time going on to condition number 2. I can say with utmost confidence right now that this series diverges because it fails condition number 1 of the alternating series test. Okay, I want to start off, example number 3 is kind of a twofold question, and I want to start off with a series that is actually not an alternating series. So just remind yourself, this is not an alternating series. There is no -1 raised to the nth power or anything of that sort. We just have a very basic general P series here. And in fact, just look at this. If you did apply the nth term test for fun, you would end up with small over large. You'd say, whoops. You would say that the limit equals 0, but that's inconclusive. That proves us nothing. In fact, we'd go one step further and we say, well, yeah, the p-value is 1/2, and that's smaller than or equal to 1, and therefore it definitely diverges, okay? However, we're going to swoop in here, and I'm going to create a new series, and it's going to happen to be an alternating series that looks very similar to the first one. It just happens to be the alternating version. And now, because it's an alternating series, we can apply the alternating series test. Condition number 1 says, hey, what's the limit as n approaches infinity for 1 over radical n? And I would say, well, that limit's 0. And now, all of a sudden, that's a good thing. It's not inconclusive anymore. That's a good thing. That means we are on track for being convergent. We would also then verify that the n plus first term is smaller than or equal to the nth term. And by the time we got done doing that, we could say with confidence that yes, this is a convergent alternating series. Well, things always look a little uglier when we sprinkle a natural log in there, but we've learned that there's certainly nothing to be afraid of. And we're going to try to sort out, it's an alternating series, so we're going to kind of throw the -1 to the nth away for now. And we're going to say, well, this part in blue is my a sub n term. It's an alternating series, so we can apply the alternating series test, which says we've got to meet two conditions. Condition number 1, the limit as n approaches infinity for n over the natural log of n plus 1. And we just have to ask ourselves, well, do we have small over large? In fact, a polynomial is considered more mathematically dominant than a natural log, and I'm going to end up saying, well, we've got ourselves large over small. Back in the day, one of the lessons we mentioned kind of this order of factorials are the most dominant, and then exponentials are the second most, and then polynomials, and then logs. And then if you want to throw at the end there, probably the weakest is either like a sine or a cosine function. Tangent's not included in that grouping, but sine and cosine would be the wimpiest. And anyway, back to our problem, we do have a polynomial over a natural log. We have large over small, therefore we get infinity, and because that's not equal to 0, we'd say that this pair instantly diverges, no questions asked. Well, I wanted to introduce one more mini topic here in this lesson before we called it a night, and it's the remainder. It's a topic we discuss as remainder of an alternating series. This is a huge topic on the free response of the AP exam, and I'll just make a note of that here. They love to throw this little topic in there, and it's usually not worth a ton of points. It might be a point or two. It's usually tucked in part C or somewhere on a free response question, but it is very often there, and it's something that we need to know and we can gobble up some nice easy points on. But basically, here's the deal with an alternating series. We still don't know the actual sum. And that's hard for me to really digest and believe, because if you think back to that alternating harmonic that we opened the lesson with, it felt like we were getting so close to the real sum that we could actually get our fingers on it, or get our hands on it and concretely identify the sum of that series. But believe it or not, we can't. And but we can get really, really close. So the bottom line is we still don't know the actual real sum, but we can get ridiculously close, and we can give what we call a remainder or a worst case scenario error. And to start off with, I'm going to let S equal the actual sum of the series. We don't actually know the value of S, but we can get really close to it. We're going to say S sub n equals the nth partial sum. Obviously, the bigger n is, the more accurate we're going to be. And then we could say that S minus S sub n is what we call the remainder. Or what I like to do, instead of remainder, the word error makes a lot more sense to me, and that's the way that I like to think of it. So, perhaps maybe the most important thing we're going to put in our notebook here tonight is right here. The error, or what could also be called the remainder, of an alternating series is guaranteed to be less than the first omitted term. You're going to hear me, I'm going to sound like a broken record some days in class where I just keep preaching first omitted term, first omitted term, first omitted term. We're going to go ahead and take a look at one example and try to put a little context to this idea. Okay, so let's take a look at this. Let's finish with a bang here. This is our last example of the night. And it says, consider the series defined as, we'll start from n equals 1 to infinity. We've got negative 1 raised to the n plus 1 power all over n factorial. And I hope you can read that here. But they said, what is the worst possible error if you use the first 6 terms to approximate the sum of the series? And I'll tell you what, off the top, I'm kind of expecting, a pretty big error, because it kind of feels like we're being lazy almost in the fact that we're only using the first 6 terms. Why not use the first 50? Why not use the first 100 if we really were serious and meant business? However, with that in mind, I think you'll be impressed with how accurate we are, even though we're only using the first 6 terms. So, anyway, the first 6 terms, okay, the sum of the first 6 terms, well, we'd start off with like this. We've got the first term would be a 1, and then minus a 1/2 plus a 1/6. That's your 3 factorial. And then here's your 4 factorial, your 5 factorial, and your 6 factorial. Notice how quickly those denominators got rather big. We're only on the 6th term, and our denominator is already 720. That's quite impressive. Anyway, the sum of those first 6 terms only turned out to be 91 over 144, which is approximately 0.63194. Okay, so we're wondering to ourselves, well, how close is that to the real sum? Okay, remember, we're going to say S by itself represents the pure actual sum. Well, how close are we? Well, we defined in the last example, we said that the real sum minus our partial sum, whoops, erase that, that should be an S. S sub 6 is, well, the difference is called the remainder or the error, and that's guaranteed to be less than or equal to the first omitted term. The first omitted term is the one that would have gone right here, but we stopped prematurely and didn't write that one down. And in this case, that would be the seventh term. What does the seventh term look like? Well, the seventh term is 1 over 7 factorial, which is about 1 over 5,040. Okay, I want you to really get in the habit of recognizing these factorials. You know, the 2, the 6, the 24, the 120, the 720. Those numbers should be a recognizable pattern of using factorials. Anyway, so our worst possible error is 1 over 5,040, which is approximately 0.0002, okay? How impressive is that? We're only using the first 6 terms to find an infinite sum, and we're only off by 2 10,000ths. That's unbelievable. That's ridiculous. So we're just going to add a little bit more to that. Now we're going to say, okay, see, we were approximating that the real sum was, pretty close to that number. So it could be 2 10,000ths less than that or greater than that. So what I'm gonna do is I'm gonna subtract 2 10,000ths and get 0.63174. And then I'm going to add 2 10,000ths and get 0.63214. And we know that the real sum, the true pure sum, is somewhere within that little itty bitty interval there. How impressive is that? So just keep telling yourself when it comes to error, when they talk about remainder, it's all about the first omitted term with an alternating series. Have a good night, and we'll catch you tomorrow.